Unit vector is a vector of magnitude 1 without any dimension. I'll give you an example. Suppose here is a block of mass m and you apply a force in the horizontal direction. Suppose there is no friction, mu equal to 0. Now this block will move with an acceleration a, which is, if f is a vector, f by m. Now technically this block has an instantaneous velocity along this direction, right? If I want to find the unit vector along this direction, so that will be this vector, any vector a, divided by its magnitude. Interestingly, this is very similar to f by magnitude of f, and this is very similar to v divided by magnitude of v. The normal notation of a unit vector is given by hat. So if you want the unit vector along any direction, suppose the direction of acceleration, so this a vector by mod a is basically a hat. Same, f vector by mod m is mod f is f hat, and v vector by modulus of v is v hat. Now I tell you that all these things are same. Why? Because of this. Unit vector doesn't carry any dimension, and this property we shall exploit throughout our mechanics. We shall use unit vectors when it's necessary, and we shall use it very often. Now these three things, if you consider a vector, f vector and v vector, these have different dimensions, that's true. But if you consider the unit vectors along this direction, suppose if I apply a force, there is no friction, the acceleration will be along the force direction by second law. So direction of acceleration and direction of force is the same, and the instantaneous velocity will also be along this direction. So all the unit vectors a hat, f hat and v hat, so a hat is equal to f hat is equal to v hat, then do not carry any dimension. You can say this as well. Suppose I choose this as the x direction, you can choose that this is I hat or I cap. Fine. Now suppose then what will be a? So if I consider this equation, a vector by modulus of a is this. Another thing I want to tell you, modulus of a is denoted simply as a, same modulus of f is denoted simply as f, and same for v. Now if I consider this equation, a vector by modulus of a, which I can write it as a, is a hat. This is also I hat. I means the unit vector along x direction. This is a standard notation. Unit vector along x is I cap, unit vector along y is j cap, and unit vector along z is k cap. That's standard notation. Now a vector then is a I cap. Now see, you have you might be thinking, what is between a and I? Means this is a product. So I tell you, there is nothing between A cap, A and I hat. This is read as A times I hat. Please remember this. For example, I tell you, suppose A is equal to 2. Say A is equals to 2. It's just a number. Of course, this A carries the dimension, so I must write it as meters per second, and this I cap is dimensionless. So all the dimensions will be provided by A. Now this 2 I cap is basically I cap plus I cap. Here there is nothing between 2 and I cap. It's scalar times a vector. Means this vector is atto times scalar. It may be 2.5 times, 2 times, 3 times, anything. So this is read as this I cap plus I cap. Now this has an operation. This is just an vector addition. Okay. When you grow old or you learn the language of vector space, you will understand that this I cap, j cap, k cap are members of a vector space, and this addition is a vector space addition. Fine. But this can be written as 2 times I cap. This 2 is not a member of a vector space. It's a field member on which the vector space is defined. I will not go into the details of that because that is not in the domain where we are studying this 11-12 physics. Still, when you grow old, those who are interested in physics, they will understand what's a field, what's a group, ring, what's a vector space, etc., linear algebras. So I will not go into that details. So what is important is this 2 I cap is I cap plus I cap. This is a operation, but here we do not have any operation. So remember this. So this is unit vectors, and we will try to represent any vector. Say any vector, suppose V is any vector. We can write it as V, the magnitude of V times V cap. V cap is the unit vector along this. So this can be, this will imply V cap will be magnitude of V divided vector V divided by the magnitude of V, or simply V. So this is an introduction what a unit vector is, and to be specific, since I say that the unit vector along X is I cap, the unit vector along Y is J cap, and unit vector of along K is K cap. So let's write that. You can have a screenshot. You can copy this as well. You can pause it and copy. Then we so take a note of this. Okay. Let's coordinatize our space. Now this is a two-dimensional space. Let me use different colors. Suppose this is X. Suppose this green is Y. Okay. And so this is a two-dimensional space, and this is an XY plane. This board is an XY plane. And the unit vector along X, this is I cap, and this is J cap. Now I need another dimension to completely coordinatize the whole three-dimensional space. So technically we must have another dimension, and that is Z. See, if you go to my videos and check that this symbol means something is coming toward you. So it's out of the plane of the board. And this symbol is into the plane of the board. Fine. Why it is so? You can think of an arrow. Suppose there is an arrow. Now this arrow, if it come toward you, and if you are looking from this side, see, you see a point, so it's coming toward you. On the contrary, if you are looking from this side, it is going away from you. You see the feather. So cross, you throw a dart or something, you see the back of the dart, and the thing is, you see a cross. So very similar. If this is the x-axis, this is the y-axis, so the z-axis will be pointing out of the plane of the board. This is the right-handed system. Remember, if you stand in the first quadrant, this is the stand in the first quadrant. If this is the y-axis, this is the x-axis. Let me fix it like this. Sorry. So this must be the z-axis. So x to y, if you stand in the first quadrant, x to y is anti-clockwise, y to z is anti-clockwise, and z to x is anti-clockwise. Anti-clockwise is a positive direction, so we move along that. So along x, so unit vector, so this is I cap. How? One thing I must mention, unit vector along z is k cap. So unit vector along x is I cap. Unit vectors along y is j cap. Unit vectors along k, along z is k cap. Remember, these are constant vectors. That means with time this doesn't change. If you differentiate these I cap, j cap, k cap, they will vanish. This is important. Point number 2 is they were constant vectors. Point number 2 is they are mutually orthogonal. I'll make a next video on dot products, but I have to mention few things on dot products, so let me mention that. So they are constant vectors, they are mutually orthogonal. That means which implies I dot j, sorry, this is a dot operation, I cap dot j cap is, if you definitely they commute, dot product is a commutative operation. So this is equal to 0. Same, j cap dot k cap is equals to k cap dot j cap, that must be also 0, and k cap dot I cap is equal to I cap dot k cap, that must be also 0. So remember things. So this is the dot operation. One thing I want to mention that as I am saying that these three are constant vector, there are unit vectors which are not constant. If you go into spherical polar coordinates, I usually teach spherical polar coordinate because it's a symmetric coordinate. Few symmetry we shall exploit in case of electrostatics and all. So those things I will mention later, not now, so that will be a little bit cumbersome. So remember, you don't think that unit vectors are not necessarily constant vectors. The magnitude is definitely constant, so direction are not constant. Let me give you an example. In spherical polar coordinate systems, which I usually teach for JE students, because handling problems with this coordinate system is very easy and less time consuming. Here you have three coordinates, and along r cap, phi cap and theta cap better to write this way, and these are not constant vectors, not constant unit vectors. So for this you have to see any specific videos on spherical polar coordinates. So I just want to mention that as I'm saying that this is a constant vector, this is not a constant vector. Achha. Another thing I want to mention, let's not go into the details of spherical polar coordinates right away. I want to mention that point number 3 is cross product. See, I cross J. So if you watch my cross product video, there is a video, you can also have it. I cross J is K, J cross K is I, and K cross I is J. It's very symmetrical relation. I cross J is K cap, J cross K is I cap, means I cross J, I J K, I cross J is K, J cross K is I, and K cross I is equals to J cap. So this is a cross product. You all cross product, reference YouTube cross product video. My ink is pen is running out of ink, so I also may stop the video. I shall do another video on dot products in the next session or in the next class. Thank you very much.